Enjoy your lecture. About what? What expectation? I was speaking to already important about the expectation in lecture session before, where you can come up with information. This is very important. But it's not about the expectations, it's about important. Your personal expectations about going down. You need to have a look how many actions you have.
All right, guys, that's got the technology out of the way. Let's do it face to face now. Right, no recap today because I'm starting a new session. And at the end of the last lecture, I gave those two magic words, neural networks. So we want to find out what goes on in an artificial neural network. And again, I'm being kind to you, I want to keep it really simple. So if you don't fail, look at your own camera. And we're going to start initially with the behavior of a single neuron and how it behaves, how it learns, and what are the problems with that. Now, at the end of this lecture, you'll know more than 99% of the computer scientists in the world, because you'll start to understand these things. Whereas the computer scientists will just type in neural networks, layers 3, nodes on the first layer 20, nodes on the second layer 40, go. And that doesn't really say very much about what's going on, does it? So, a neural network. The reason we want to look at neural networks, A, they are fantastic data processors. They started in the 1940s. Alan Turing devised the first single instruction, single data machine to crack the Enigma codes. 1942. He was also at the same time thinking about neural networks. And he invented a test in 1942 known as the Turing test. And it was quite an obvious test. If I'd have been around, it would have been called the Stollen test, but that wasn't. So it was quite simply, if you were communicating with somebody, by telephone, for example, and you couldn't tell whether the thing on the other end was a human being or an artificial system. If it was an artificial system and you thought it was human, then that artificial system must be intelligent. Not a very rigorous test, but quite interesting. So, why are we interested in neural networks? Well, it gives us all the processing we do as humans. Everything we experience is a combination of electrical signals. So, wow, you are important people. Because you're controlling the whole of humans. Yeah, everything you do. All I've got to do to turn your body off is just to cut a few nerves in the spinal column in your head. And you're a paraplegic or quadriplegic. Can't cut them all. Why can't I cut them all? Because there's a few signals which are keeping the fundamental system going. And what is one of those fundamental systems? The heart. So the old brain is producing a pulse, roughly every second, to the heart, to cause the muscle to go each time you get a shock. And that will squirt a bit of juice around. Now, isn't that amazing? 1 pulse a second, 3,600 pulses a year. No, an hour. Whoops. Times 20, 60,000 pulses a day. Times 400 roughly, 24 million pulses a year. How long are you going to live? 100 years? 24 million, 2.4 billion pulses. Keeping it going. And it doesn't often need servicing. Sometimes you have to clean it out a little bit and put a little bit of metal in there to keep the walls open. So basically it goes on for 100 years if you're lucky. Wow, impressive. The brain doesn't need programming. We somehow learn this mystery thing of learning. Seeing a picture, seeing your face. I've forgotten your first name. What's your first name? Norman. Face in, Norman in. And somehow I make the connection. And that's Norman. No, it's not Norman. That's Norman. The speed of the brain is pretty slow. It's not electronic speeds. In fact, it's only about 10 meters a second. And I played around with a little joke last week about someone trying to catch the pound note, let him catch it, and then overloaded his brain by distracting him, and he dropped it. So the brain is pretty slow. It's a slow processor. But what it is, unlike a single instruction, single data machine, which is a conventional computer, it is a parallel machine. And we find parallel analysis quite difficult to handle. We like to do things step by step. We can follow them along the computer program. Do everything at once. Hey, that's quite a challenge, but that's what the brain does. So, we want to get some clues about electrical processing, signal processing in a natural cell called the neuron. Okay. Let's have a look at one. Right, there is a representation of a single cell. It has inputs, roughly 5,000. I use that one because it's a better diagram than I can draw. This is the output here, and presumably that yellow stuff is some insulation. Yes, you've got that basic electrical crystals operating in the system. And the output is then distributed, multi-points, and they will interact with the next neuron here on the inputs. So we can provide information forward and presumably information being fed back. So that is a neuron, and you will have about 10 to the 11 of those in your brain. 100 billion in English or French or Swahili or whatever. Quite a big number. And another thing about the brain is it's resilient because those cells are dying day by day. You carry on. So it has fault tolerance, it has redundancy. All these sort of problems we don't have in a computer. If I take your phone, there you are. If I take this phone, and I've got my little Black & Decker drill, and I drill a hole through it, chances are the phone will stop working. Take your head, drill a hole through it, pretty painful, bit messy, bit gooey, but it won't destroy the brain. It will reattach. So built-in testability. So, or fault tolerance. So that's the potential of the brain. Now we don't want to copy the natural system exactly. We're just using it for inspiration. People have tried to model that device to get exact input-output waveforms. Don't see the point of that. They can use leaky integrators and goodness knows what, and it's a whole paraphernalia to try and get waveforms on the inputs and matching waveforms on the output so that would behave as a natural neuron. But no, as engineers, we can make approximations. And if we get an approximation to the model, it will have some of the properties of the natural system, some inspiration, and we'll see how it behaves, see if it has any emerging properties. And that's the key. We don't want to clone or make more brains. There's a much easier way of making new brains, which you all know about. He's straight on the ball there. And also, if you want an existing brain, they're quite cheap. I think they've now gone up to £9.50 an hour, which is the latest minimum wage on the budget a couple of days ago. So brains can be bought or acquired fairly cheaply. But getting to understand how that total system is a challenge. And I said last week in introducing the topic, don't be bamboozled by neurosurgeons and medics. Anybody got parents who are medics? Oh, go out. Leave. Don't record this. They think they've got more powers and more understanding than they have. And if they were trying to analyze the brain, they'd take the whole brain, they would stimulate it, they would find areas of activity, they say, hey, I've found the vision center, I've found the sense center, I've found the emotion center there. That's how it works. No, it doesn't. As an engineer, I could do something better than that if I was doing a top-down design. I could take a volunteer, you, for example, you look like a typical human being. You'll cooperate with research, will you? Yes, of course you want, she's volunteered. Take her in the lab, get one of those little tiny circular saws the medics use, zip round the top of the forehead, carefully, cut the skull off, take the skull off, look inside, there it is, all this throbbing grey matter of 100 billion cells, and I want to see what happens. I'll get a tiny little battery, don't need a big car battery or whatever, only need a few 100 millivolts, and I put a contact across there, the leg goes out. I put the contact somewhere else, you hit me. And we could relate electrical stimulation to people. Again, we're not understanding what's going on, it's still top down. We could, of course, go to animals. Don't particularly like the idea myself. I like animals. But it's the same problem. The complexity of an animal brain is almost the same. A chimpanzee is about 10 to the 10 cells. Mechanical engineer is 10 to the 9 cells. A spider is 10 to the 7 cells. They are still hugely complex. So what we're going to do is we're going to start off with one single cell, and we are going to try and model it. Right. Let's assume that there are voltages coming in on the inputs, and they combine in some function there, which produces a voltage here, which is then transmitted to other cells. So the model I'm going to take let's have inputs. I1 down to IN. And they are going to be voltages. And again, it's looking like a vector. We've seen vectors in distance classifiers. We can call that a vector of n elements, where I1, I2, I3, I4, IN are the individual elements or measurements. Now we know that each input might have a different effect. Some have more effect, some have less effect, some might inhibit and add to the response, some might inhibit and subtract the response, some might excite, add to the response. So let's now include some operator. No, in fact, I'll draw those as circles. More conventional. And these circles are numbers which change the value of the inputs, and they are called the weights. And this would be W1, W2, W3, W4, Wn. And again, it's a vector. We call that vector W. And if we want to make the effect of the input bigger, the weight becomes bigger. If we want it to be smaller, the weight has to be less than 1. If we want it to enhance, it's got to be a positive weight. If we want it to inhibit or reduce the output, it's going to be a negative response, a negative value. And those weighted inputs go into another device. And we want to now get the overall effect of those weights of the inputs. What is the easiest way to combine? Multiplex. Multiplex, no, that's putting each individual one through one at a time. Glad you remember something from level 1. Another simple operation to combine them. Add them. Adder. So that will give a summation of the weighted inputs. And usually there is a threshold following that, which will determine if the pattern is giving above or below a certain value of the summation. The main processing is going on at the output of the summer, but the decision comes by applying a threshold here. So that is a model of a neuron. And so this would be a summer, and this would be a threshold. And normally we call that S, and let's call that response R. Okay. Now that was a concept, and you go back right to 1950. This was a model proposed by a couple of Americans called McCulloch and Pitts, sometimes known as the McCulloch and Pitts model. And it was sometimes given a name which is commonly used today. It's a made-up name. It's called a perceptron. And that is the name of the stick and the individual cells. Quite often you'll see them referred to as perceptrons in papers. Right. The first model, 1950, and this model was 1950, a long time ago. Even I don't remember it. And how do we get weights, quantities that are going to change what are effectively voltages coming in here, and consequently currents flowing from the voltage? So what is a way we can change a voltage, or a current flowing from a voltage source? Resistor. And if we want a large current to flow, we reduce the resistor value. If we want a small current to flow, we increase the resistor value. So the idea of these weights in a model, electrical model, these inputs, let's call them I, would be regarded as variable resistors. That would be R1, I2, R2, right the way down to IN, and that would be Rn. And again, they go into a summer, and a threshold, and let's stick there with the modulus. Right, how can we change a value of a resistor? The material. Yes. So can you simplify that? A volume control on your amplifier, if it's not fully digital, what is that? It's a variable resistor. And a variable resistor in the old-fashioned way has a knob which you turn up. And if you've got your Marshall pop amplifiers or whatever, it goes up to level 11. That was thought to be an ingenious amplifier with more power than goes up to 10. Marshall's wrong on that, but the problem is still bought the amplifier. So you have to turn the volume control before the variable resistance changes. Okay, well, we don't want to have people involved. It's got to be an artificial system. So what can be used to turn the volume control? I can do it. I'm not there, and I want to turn it remotely. What do I need? Oh, no. This is 1950s. A motor! So these can be motors. And just to show you that this was not my fantasy, this is 1950 in Princetown in America. And they built one of these machines. And if I can get this thing to work. No CCD cameras available in those days. So they built a CCD camera which was going to recognize characters. There's the example of the letter C. There's a couple of lights and there's some scanning device in the middle there that is actually taking information out. That was the world's first CCD camera, or pixel camera. Right, that was the input. It was 16 by 24 pixels on that character. And it went into a neural model, 16 by 24. Each element was a pixel. 16 by 24 is 384, is it 364? Work it out for yourself. It's 16 by 24. They would have that number of inputs with that number of variable resistors, each driven by a motor. And the machine they built looks something like this. And there was a very smart PhD student of the day in 1950s Princeton. These are the individual motors, 1, 2, 3, 4, 5, 6, 7, 8, so they're in racks of 8. And there was 364, 384, whatever 16 by 24 is, in a downgrade rack. Why were they building it in 1950? Because IBM at that time was saying the world's market for computers is 6. Computers virtually didn't exist. So if you wanted to experiment, you had to build the rest of them. And the people at the Princeton, they'd just finished setting up and prototyping the atomic bomb. And you've seen the films of the atomic bomb going off at Los Alamos. That must have been a fantastic experiment. You know, they got all the troops about 5 miles away sitting back in deck chairs with dark glasses, watching this as the thing went off. I nearly killed all of them in the end because the radiation didn't realize it. But what an outcome from working out the principles of the atomic process, blowing a cloud of uranium into a globe of uranium, surrounded by beryllium to keep the radiation in, and getting a chain reaction, and woof, it went off. So that must have been really the world's most exciting and possibly deadly experiment. I wish I'd been there, but I'm glad I wasn't. But having done that, they wanted to do something really exciting. So they started to look at neurons. And this was the machine they built. And how was it connected together? It was connected together by a random array. Again, looking at biology. And that was the connection panel for these racks, which contain the motors. So, sadly, the Mark I perceptron, as it was called, it didn't work when they built it. Oh, bugger, they said. But of course, by not working, it made them think about what they were doing. And that led to more discoveries. So, any of you going to do PhDs, and if I was supervising your PhD, and you came to me and said, I've got these fantastic results, it all works, it's fantastic, I'd say, interesting. But if you came to me and said, the damn thing isn't working, now that's more exciting because you ask the question, why isn't it working? And that's where you make progress. So the fact that this machine didn't work was, in the end, a good thing. Right, how does it work? Well, let's go back to get back the reveal now. Let's get rid of that. Let's take our output there, S. This is for n dimensions. Let's simplify it as much as we can. Let's reduce it to 2 dimensions. Well, before I do that, let's work out what S is doing here, the output S. S is equal to I1 times W1 plus I2 times W2 plus I3 and so on. It is the summation over all dimensions, I equals 1 to n, of W I. And that is an important equation. It's the summation of product pairs, the product of the input and the weight. And I'll come back to that a little bit later on. So that's an important first relationship. Right, now let's go down to 2 dimensions, as simple as we can get it. And the model would simply be an input I1 and I2. We would have W1 and we would have W2, and we would have a summation, and we would have a threshold. So that is my 2-dimensional model. Right. what actually is going on in this model? Yes, it's a summation of the product pairs, but some of you might recognize that as a mathematical identity. Can anybody, thinking of vectors, can anybody tell me what that is?
Dot product? Dot product?
It is the
Dot product.
dot or inner product. Well done. So I can write that now as being equal to vector W dot vector I. So the model is creating a dot or inner or scalar product of vectors. Now in 2 dimensions, we can simplify this. In 2 dimensions, the summation I equals 1 to n over wi I equals w dot I, which also equals in 2 dimensions the mod of w, the mod of I, and the cosine of what? Of the angle between them. Let's call that theta. And that is great, because we can now draw this and see what's happening. So that is the function in 2 dimensions. In 3 dimensions, yes, it's a solid angle, a bit more complicated. If we go to multi-dimensions, it's a hyperangle, whatever that is, and you can't imagine it. But we can see in 2 dimensions what's happening. So we can now draw this. So let's have dimension 1 for all vectors and dimension 2. If I have a weight vector, let's have a weight vector there. That is my vector point in 2-dimensional space. This dimension will be W1. This dimension will be W2. Let's have a pattern, an input. Let's call the input I, down there. And that's a vector point in 2-dimensional space, which represents I1 and I2. And what's the mod? The mod is the distance from the origin to the vector point. So if I actually draw the vector, there is the vector. The length of that line is mod W. Right? For the input pattern, the vector is that point there, and the length of that vector is going to be mod I. And as my ingenious guy already told me, which I've forgotten, theta is the angle between them. Right, so that's what's happening in 2-dimensional space. If I go back to the model now and look at the threshold and set the threshold equal to 0, which means I'm detecting whether I get a positive or a negative response from this model. If the threshold is 0, then the threshold is controlled by theta, because we're looking for the output being positive or negative. Mod W can never by definition be negative. Mod I can never be negative, but the only thing that can be negative is cos theta. And when is cos theta negative? When it goes above 90 degrees and less than 270. So when is cos theta 0? 90 degrees. So if cos theta is 0, then if I draw this again, that's a W there. Any pattern, and remember I'm only drawing one quadrant, these inputs can be negative, so we can have 4 quadrants of the dimensions. Then, if that is W, we can draw a line in the space which is at right angles to the weight vector, goes through the origin, and any pattern, any I on this line, will give a 0 response. If it's on this side, if an I up, an I there, they're used in blue, wasn't it? And a green. If I have an I there as a pattern, I1, that will be a positive response because theta will be less than 90. If I have an I down there, the response is going to be negative because theta, the angle between the weight vector and the vector of the pattern, is going to be greater than that. So we can get a different response depending on the angle between the weight vector and the test patterns.
Wouldn't it be positive there?
Hmm?
Wouldn't it be positive there?
Where?
Here.
Here?
Yeah.
Right. Mod W positive, mod X positive. That angle is 120 degrees roughly.
Which is less than 270.
Greater than 90, less than 270. Negative. Cos theta is negative. Yes? All agree? Right. So, hey, we can use this as a pattern classifier. So a 2-class pattern classifier. Let's take and draw the 4 dimensions. Dimension 1 and dimension 2. Well, we're talking about replacing exams with a neural network that will determine whether you're going to pass or fail. And I suggested that 2 measurements might be the number of hours studied and the number of hours night classes. And we came to a conclusion that we would have a class of patterns here. There they all are. That's last year's cluster. And they were the guys who passed. And they did a lot of study and very little night clubbing. And then, of course, there's you lot who are down here. There's a lovely little cluster there. And they're doing a little bit, of course, you're on this as well, you are, so you're down there. No study at all. This person is not here. So we've got that cluster down there, which is different. Right. Looking at that, which we can do in 2 dimensions, we can draw a decision surface which will separate the red from the green. And let the decision surface go through the origin. The decision surface would be that line there. It's not the only one. There's tens, hundreds, millions, depending on the resolution. It just has to be between those 2 known patterns, and those known patterns. And of course, that decision surface can be defined by a weight vector, which will be at right angles to it. And there would be my W, which would be W1, and that would be W2, which will be negative. And if I can find that weight vector on a set of known patterns, these were last year's passes, and these are last year's failures. If I can find that weight vector, then maybe I can use it to classify other patterns, because if I put in some unseen patterns, which is the whole point of neural network classifying new data, if I put pattern in there, and I've got those weights, what is, and this is going to be the plus side of the surface, that's going to be the negative side. There is steep at 90 degrees, and of course down here, that's where your 270 degrees comes in. There will be 3 right angles there, and there, that will be 270 degrees. I do like 250. And of course, this pattern will give a response. It will be positive. It could be associated with this. A pattern down here would give a negative response. So it is classifying unseen data on the basis of that seen. Right, it's doing pretty well the same as a distance classifier. There's a decision surface there, that's causing the behavior, but you don't have to know the decision surface, you just get the response from the model and see if the output there is positive or negative. That's how the classification is done. And of course, there's a lot less processing to do, because in n dimensions, if that is an unknown pattern x, let's call that x there, to classify x, I have to calculate the summation I equals 1 to d of w I times xi. And so it is a multiplication and a summation for one pattern at weight vector and the input. So we don't have to do all the distance calculations for all the reference patterns and find out which is the shortest. It appears to be behaving like a distance classifier, but it's using a weight, and that weight, the response to the weight for its threshold is 0, positive is one class, negative is the other class. And of course, you could change this around arbitrary. If I wanted this class to be the negative and this to be positive, where would the weight vector go? In the exact opposite direction. Yes, I could have a weight vector going down there. So it doesn't matter how you assign the polarity of the classes. Right, so that's interesting. But the question now is, how do we obtain W, the weight? Now, for 2 dimensions, no problem. We draw it, we look at it, we can write it down. For example, the weight vector there would be, that would be about minus 10 plus 8, whatever that quantity is. But you could do it in 3 dimensions, but you can't inspect the pattern space in 4 dimensions at hyper volumes, 5, 10, 15, 20, 100, 1,000, million. So you've got to rely on the mass to do it. Okay, finding the weight vector. And this is the key process. I think it's up there. That is a big question. And the principle started off with that original machine in 1950. It's an obvious way of finding the weight vector. It might have some parallels in biology. Start off with a random weight vector. You've got to start somewhere. You've got to be born. Yes? Define the 2 classes, positive, negative, pass, fail, good, bad, letter C, not the letter C, whatever the decision is. Test it on a known pattern, the training. Note the response. If with the random weight vector, the response is what you want, the correct response, so a 50-50 chance it will be correct, stick with those weights. If, however, it's a positive response you're looking for, the student who's going to pass, and it's saying he's going to fail, but you knew he passed from last year, you've got to know your training data, then you've got to change the weight vector. Because by changing the weight vector, let's go back to the original weight vector which was out there, by changing W, if I move W, then the decision surface moves, because they've got to be at 90 degrees. And the simple way that they started off training these devices was a strategy first sort of identified by a guy called Donald Hebb, and it's called Hebbian learning. And again, it's common sense. If I'd have been around at the time, I would have thought of it, so would you. It says if the system is making a mistake, change your weight elements. And when you make a change to the weight elements, look at the output of the neuron, and if it is moving in the right direction, suppose it was giving a negative response, and you want a positive response, you change the weights, and the output becomes less negative, stick with that value. If, however, you change your weight, and it makes it worse, go back to the original weight. And you can devise all sorts of little games for kids and animals, where you have two knobs and a bowl of food that moves around, and you tweak them. As you tweak them, the bowl moves. You can gradually turn it the wrong way, it goes that way, no, go back to where we are. You can tweak the thing and get to a target, or a needle on a meter, or whatever. So that's the idea of Hebbian learning. You make a change. If the change improves or reduces the error, stick with it. If it makes the error worse, go back to the value you had before. So you're sort of optimizing by tweaking. And that was Hebbian learning. So, how are we doing for time? I've only got 5 minutes left. So, I haven't got time to start on an algorithm yet, but let's just show graphically what you might do with Hebbian learning. Let's take two patterns. Let's have red and blue. And I've now got, this is training. And have blue down there. If I start off with a random weight vector, let's say the weight vector is there. There's W there. And so the decision surface will be right angle. Right. I test on, this is going to be the positive class, this is going to be the negative class, and let's change these values. That can be, let's call it P, and let's call it N for positive and negative. If I first of all test with the random weight vector, the initial weight vector on P, mod W is that, mod P is the line there, theta is very small, the angle between them, it's going to be positive. That weight vector has this P on the positive side. No change. I now test on the negative pattern. Again, mod W doesn't change. I had to change it from the last time. Mod N, the negative pattern. The angle is still less than 90 degrees. It's positive, it's wrong. So I've got to change the weight vector so that this becomes on the negative side of the pattern. So, estimating it, if I move the weight vector, say, to this position here, that will be that weight vector now. There's the weight vector there, and the decision surface will be at right angles to it. Positive, correct, because theta will be less than 90. Negative, but I've only trained on two patterns. I haven't got very much information about the class. I might well find that I've got another P pattern there. So when I now include a third pattern, correct, correct, incorrect. I've now got to change the weight vector to get this correct. And it's a matter of moving and converging on a solution. And a solution won't always exist. If I have a problem like this, taking those individual patterns, yes, we can converge on a weight vector. There's a decision surface. There is a weight vector solution. But if I have a problem like this, two perfectly distinct clusters of vector points. So remember, I'm looking for a decision surface coming from the origin. There is no way I'm going to get a straight line, a linear surface that will have the blues on one side and the reds on the other. And that's known as the linearly inseparable point. Linearly inseparable. Can't separate with a linear function, in the case of 2 dimensions, a straight line. And of course, we can see that in 2 dimensions. If you're doing it in 5, 6, 7 dimensions, you can't see what's happening. The thing would just change. The weight vector would continuously update as you go through. You have to go through the patterns time and time again to make sure new errors haven't been introduced. And it takes hours, days, months, sometimes years, sometimes never to converge the solution. And that's a case where a neuron doesn't work. And in the early days, people didn't realize that. This was the problem with the original machine, that original perceptor in the 1950s. The character recognition problem was not linearly separable. And they had to modify it, which led to better neurons. So if you don't succeed at first, try again. So that's the idea of what's happening. The weight vectors are moving in space to classify patterns of one class on one side of the surface, another class on the other side of the surface. And this simple model will only work for these linear patterns. In fact, it won't work for all linear patterns. An example I'll show you next time we lecture. If I have this problem, where that is one class and that is another class, that is perfectly linearly separable. But the model so far, the decision surface goes to the origin. All you can do is rotate the surface about the origin, and we will never converge to the reds on one side and the blues on the other. But that problem has an easy fix.
Can't you just change the origin? Can't you just change the origin?
Yes. Yeah. And exactly how do you change it? See if you know what it's talking about.
Shifting the data points.
Oh, you can't see the data points. Remember, this is in multidimensional space. You actually have to increase the dimensionality. Just imagine that. I'll give you the solution here. If that was the origin of the weight vector in 2 dimensions, if I put it in a box and make sure that that's going across there, there's a box. If I have this as the origin, which will be 3 dimensions, x, y, and z, then the weight vector is a point which is oscillating in 3-dimensional space. The decision surface is a plane in 2 dimensions at right angles. How about this for visual aids? So there's the weight vector. As the weight vector moves around, the plane moves always at right angles to it. And if we have a weight vector heading backwards there, the plane comes from that point, it comes through the space, and it cuts the decision surface where the patterns are as a line. So the plane comes whoosh, out here, heading in an angle, and descends down to that point there. My drawings are pretty awful, but think about it. And that will solve that problem. So that, I'm stepping ahead of myself, I'll go through this in more detail in the next lectures, but that is known as biasing the neuron. And ask any computer scientist what biasing a neuron is, and they won't give you the right answer, because they don't know. But the patterns are still 2D. And you add a constant element to the pattern, and the weight vector is 2D. 2 weeks time I'll go over it. Okay, any questions? It's amazing to think about this. Are you getting excited by this? You can to be better than most Elon Musk employees. We can employ you guys and really know what it's all about.
How do you do?